So today we're doing another one topic video, I'm guessing. That is going to be on p-Hall families. So definition. Let X, don't get ahead of myself here, let X be a set a p-Hall family. I don't know what a p-Hall is referring to. I tried looking up, I couldn't figure it out. P-Hall family in the free magma of X is a totally ordered subset of MX H such that, first off, we have that X as a set is contained within H. 2, for two elements in H, if one's shorter than the other, then that one is less than the other. Three. So we have U, an element of the free magma, which is not just an element of X, with a decomposition which we recall is unique. U equals V times W in MX, of course. And then U is an H, if and only if, and then there's two conditions here. A, V is an H, V and H are in W, V and W rather are in H, with V less than W, which, as we saw before, means that, I believe it means that, no, it doesn't necessarily mean that W is longer than V, but if not, either W is longer than V or W is greater than V for the in homeomorphism class thing order. And then either the second half of W is either in X or it decomposes once again uniquely, with both halves being in the p-Hall family, which includes all of X, as we saw, and the left element is less than or equal to V. This is a very kind of abstract definition. Like, it's not hard to see if a given thing would be inside a p-Hall family, but it is kind of bizarre as a definition, and it comes with a lemma. every set X has a p-Hall family. And we prove by induction. So actually, the proof I don't know is by induction, but we define by induction that this set h to the n be the intersection of h with xn. How do we do that? Well, we take h to the 1 to be equal to x, with a total order. We do it on both because they're equal, and it needs to be total, and write that in. Then each hn is defined by h1 through hn plus 1, and so that it meets the three conditions above. For elements of length less than or equal to n minus 1. Choose any total order on h to the n, and put u less than v if u is an h1 hi, v is an hn, and of course I is less than n. Then H being the union of RHN is a p-Hall family. Alright, let's look at an example. We're going to let X be a set with two elements. We'll just call them X and Y. Then H1 is going to be equal to, we saw it being just H1 is equal to X with an order on it. H2 has to be elements of length 2, and we can't meet 3a ever by that, so H2 is just going to be equal to H1. H3 is equal to well, we need elements of length 2 on our right, because we need to be length 3 total, so it's going to be 1 on the left and 2 on the right. It's going to give us 3a. And either w is an x, which is not possible, or it splits into 2 elements with with w prime being at most v. So that gives us each 3 has to be x, and then x, y, and then y, x, y, with x, x, y less than y, x, y. Right, continue on with h4. Well, what can we add to the left of x, x, y? We can add an x to the left of it. We can add a y to the left of it. And to the left of this y, x, y, we can only add a y, of course. And I'm not going to write out all of h5, but to the left of this one, we can of course have an x or a y. To the left of this one, we can only have a y. To the left of this one, we can only have a y. And then for this is going to be kind of ambiguous notation. And then for in h3, we can have x, y to the left of either of these. And keep in mind, we can't just have the atom in the middle loose, so we need to have double brackets here. And this continues on in the same way. And why does this matter? We have theorem here. If H is a p-Hall family, in MX, its image, that is the image of its components, in LX makes a basis. Okay. It looks like M. Hall was like the guy who did this. Okay, so now we're going to write here, let H in our set H with image H bar in LX. Theorem is equivalent to having both that, first off, the image of our set H generates, I'll write it, I guess, better. The image of H in LX generates LX, and the elements H bar are linearly independent. They cite proofs of part 2, such as M. Hall's The Theory of Groups, Ewitts Die Unterringe der freien Lichen. I think there might also be a proof in Bourbaki, but we won't be seeing that in this examination of it. We will only be showing a proof of part 1. We're going to let Lx prime be the K module generated by our collection of H bar. Since X is in Lx because it's in H, all we need to show is that Lx prime is a Lie algebra. That is, H1 and H2 being an H implies that the bracket of their images is in Lx prime. We proceed by double induction on the length n, which is the length of H1, H2, so it is the sum of their individual lengths. And for a given n, on the infimum of H1 and H2, because keep in mind that H is in an ordered set, totally ordered. We also assume finite x. This is with the general case following by passing to an inductive limit. Okay, and assume, finally, one last setup bit, assume without loss of generality H1 is less than H2, because the Lie bracket is antisymmetric, so we can just swap their order, and if it's the same element going in both ways, it's just 0. So by alternativity. So alternativity takes care of everything except for this space, H1 less than H2. Okay, first case. Let H2 be an X. So that H1 is an X, because keep in mind that H1 is less than H2, and X is kind of at the bottom of our order, because we're ordering first and foremost by length. So H1, that puts H1 in X. Thus H1, H2 is in H. So H1, H2, the image of their product is the bracket of their images. So one side note, looking at this, I'm wondering if this one is supposed to be... No, it's not. Never mind. I was wondering if it's supposed to be X, Y. But that would work, because X is less than Y, because we're partial order. But Y is also going to be an X, because of 1, so yeah. That would work. Should this be XY? Then here in this case we have okay. And so we have that as our first case anyways. Our second case. H2 is not going to be an X. Let H2 equal to H3, H4 with H3 and H4 in H, implying that H3 is less than H4 given our rules. And we have subcases to examine. Either H3 is at most H1, so then H1 times H3, H4 is an H, in which case the bracket of H1 and H2 H2 we can expand into the bracket of H3 and H4. Which is the image of H1, H3, H4. As desired. And B, H1 is less than H3, which remember is by assumption, by construction, less than H4. Then we get the Jacobi identity as 1H2 equals as above, is equal to 1H1 bracket with h3, h4. And this is equal to, we're on the other side of the equal sign, so there should be negative of h3 with h4, h1, but we're going to swap their order to give us h1, h4, and that gets rid of our minus sign. Minus, then h4 we're going to present as usual, h4 with h1, h3. Now, the length of h1, h4 is less than the length of h1, h2, since the length is going to split in part into addition on these things, and h4 is a substring of h2. So by the inductive hypothesis, h1, h4 equal to the sum of C alpha, H alpha bar for H alpha in our Hall sets. Then we get the length of H alpha is equal to the length of H1 plus the length of H4, because that's how it's splitting apart. So the length of H alpha, you see, is greater than the length of H1. So by definition, L alpha is greater than H alpha, not L alpha. By definition, H alpha is greater than H1. As H1 is also less than H3. The infimum of H3 and H alpha is less than H1, which is the infimum of H1 and H2. By the induction hypothesis, we see that H3 with H alpha, these are the images of course, is a linear combination of H's. Similarly, replacing H3 with H4, we see that H4, H1, H3, all brackets, is a linear combination of H bars. So everything reduces down, and our induction is complete. This is gonna be a kind of a short episode, I think, but I don't want to start a new topic because it's big and long and scary and I'm tired. So one thing I might do, actually, now I'm thinking about it to pad the episode out, I'll try to answer like what all these free things look like. I'll just kind of like spitball here. This is not a formal discussion. I might get some stuff wrong, but for this informal discussion, let x be, say, x, y, z. Now, the free magma of x is going to look like essentially binary trees. So we're going to have like something like the root has two nodes, which either has an element or another node off of it. And go like something like this. So what this would look like here, then y, z, if you have two elements, I'll go bottom to top. If you're combining two elements from X itself, you can just write them as like this. Otherwise, you need to bracket like where they came from. X, Y, and if you have, both of these have more than one term in them, so this is what elements of the free magma look like, essentially. This is what MX is. The next free structure we defined is the free algebra. A of x, which is essentially, I'm gonna also for this discussion, I guess we should set our base ring here. We're gonna set it to the integers. And so this is going to be the sum of some elements in K. We'll call it like CMM is how we wrote it, where CM is an element of our base ring, in this case Z, and M is an element of MX. So essentially, in this case, it could look like 3x plus 5, x, y, z, z, minus 7, right? So essentially you have some number and then just some string of elements in some element in your free magma. How this works, addition is component-wise. And multiplication also is going to split linearly over the addition. But if you have, like, say, 4, if we're going to multiply, say, let's do something like 3x plus, I don't know, yz times, I don't know, 2, xy. Well, 3x times 2xy, you just multiply the scalar components here, so that's going to be 6, and then we just do our magma multiplication, so it's going to be x, and then xy. And likewise, our second component here, we're going to have 2 on the left. Right, is more than one element, so we need to bracket it. Y, z, and same for our component on the right, xy. Note this is all to form an element of our ring and an element of our free magma. That was the second free structure we defined. What is the third? L of x is the free Lie algebra. And it's a reminder, this is of the form ax over I with I generated by elements of the form like xx and of the form Jacobi of x, y, and z. So essentially, this looks much like the free algebra, except that whenever you have a string like, have two adjacent elements. Whenever you have like a square in it, that term is going to disappear. And likewise, you can apply the Jacobi identity. So like, if you multiply, say like, notice that x plus y has to be equal to 0. And so you can run through the performance we saw before to get anti-commutativity. So like, let's say I want to multiply x times, I don't know, 3x plus 2y. Well, we're going to get 3x squared, but x squared is in our ideal, so that's going to disappear to 0. Like on the term on the right, we get 2xy, and keep in mind, from x plus y squared being our ideal, which we're going to get this is equal to negative 2yx. So essentially we can treat this multiplication, our magma product here in the free magma, as a Lie bracket, is what makes this a free Lie algebra. The free associative algebra, whoops, that's not how it goes, k to the x. This is the free K module with basis x, which is so this is the free K module with basis x. Oh, so this in this case would be like 3 copies of, in our example, keep in mind our example is z, k is z, and x is an element x, an element y, and an element z. So this is isomorphic now to z cubed. It's not like the above, we don't, it's almost kind of like, looks like our free algebra, but keep in mind, first off, it's a module, not an algebra, so we don't have this multiplication. And so it's essentially going to look like, you could write it as like 3x plus 2y plus z if you wanted. Or you could write it as like 3 indexed by x, 2 indexed by y, and 0 indexed by z. And it is a module. So your only functions are addition, which is component-wise as usual, and scalar multiplication, which is also just going to be component-wise. So that's not too exciting. And the last topic item we have is the associative algebra on X, which, if you recall, is isomorphic to the tensor algebra of K of X. This is going to, what is this going to look like? Well, this is the tensor algebra on K of X, so it's built up from like, you know, it's going to have like 7x plus 3y plus, I don't know, 11x tensor y plus, I don't know, 5z tensor z. And always addition is component-wise. The multiplication is the tensor product extended linearly to the entire thing. So we saw before we had this map, capital Phi, from the universal algebra of L of x to this is an isomorphism. And we also saw that there's a map phi from L of x to associative algebra of x, which is isomorphic onto the subalgebra of the associative algebra of x generated by x. Oh yeah, and we also have, I guess I should add in like 1 plus, because we have the base ring present here. So, and yeah, that's, I think, a good overview of all the universal structures we've seen so far. I'd like to be a bit more clear on maybe the difference between an open question. I guess I'll write it. No, what? I just want to know exactly what the comparison between Lx and the associative algebra of T and the associative algebra, free associative algebra of x is. Like, I mean, we have the lemma that we proved from before, but like, so we know that Lx is going to have our Lie properties essentially from our bracket. The difference between Ax, so hang on, in Lx we still have elements of the form like 5x yz is an important example, or like 3xy yz is probably a good example. And if we don't have anything like that in the associative algebra, that's just going to be like we have elements of the form 3x tensor y tensor z, but we don't ever have this. Essentially, the free associative algebra is, as it would suggest, associative, where the free Lie algebra is not necessarily associative, which makes sense given their properties. So I'm pretty sure the map phi, small phi, from Lx into the associative algebra of x is going to send, basically gets rid of the brackets, I think. It's the subalgebra of the free associative algebra of x generated by x, because we have a copy of x inside. Maybe I gotta spend a little more time thinking about this kind of stuff, but hopefully this should give a bit of insight, maybe. Hopefully. More to me than to any viewers, because I don't know how comprehensible any of these lessons are, but it's helping me, I think.